Jim mentioned in his video, he is currently on vacation, so he cannot attend this Q&A session. For the Q&A session, mainly, if you have questions to Greg, he is online here, and please use this Q&A that button, right? So you click that and add your questions there.
I can probably ask some, I can answer some Apple questions too, but I should be careful what I say.
Okay, yeah, that'd be great too. Okay, so the I think so. Greg, so should we still ask Kamaneth to ask a question? So let me check. Yeah, all right, okay. So
maybe
we hear the
maybe I can have one question to Greg as an open question. So Greg, you have been using CALPHAD so many years, and you experience people developing the CALPHAD and then using the CALPHAD and further extend CALPHAD, right? So I mean, we feel a lot of need of the CALPHAD with more and more development, even right now with the machine learning and so on. So what do you think, if you look at like in the future, the CALPHAD community, right? So what do you feel the challenge of the CALPHAD approach, especially for development of the database? Because I feel that a lot of people now using the CALPHAD to apply, but we also feel the need of more and more database and more accurate databases. Do you have any kind of common experience and the insights share with us?
Yeah, what I've been advocating for an MGI 2.0 is to really look more closely at the Human Genome Initiative model. They set out to measure, I think, 3 billion base pairs, starting from it being impossible. And they brought down the cost per base pair by orders of magnitude by developing the high throughput experimental techniques that over 13 years got the average cost to $1 per base pair, right? And I would say in the structure of CALPHAD, we really get our most accurate inferred quantities from tie lines, because we can measure compositions to high precision, and that really defines the free energies to higher precision than we can get from either DFT or calorimetry. So I think the base pair for us is a tie line, and I think it'd be an appropriate goal to develop the techniques to measure tie lines and get it down to $1 a tie line. And so I really think that the future is the new high throughput experimental techniques. And I have a proposal in the works to get started moving down that path.
All right. Hopefully that proposal will get funded.
I hope so.
All right. Okay, that's great.
I imagine we'll hear more from JC on that topic, I think.
Okay. All right. So the next one will be the question from Kamaneth. So Kamaneth, you are now the co-host. Can you share your camera and also ask your questions?
Hi, I'm Kamal. So I actually have like 2 questions. So first question is that, like, in your talk in the beginning, you mentioned the CALPHAD is all about this non-equilibrium dynamics. So, but like in the recent like processes, like in the additive manufacturing, so we are like the processing conditions are so far away from equilibrium. So how reliable are the free energies which you predicted, which CALPHAD methodology predicts in this kind of calculations? For example, we can have like for example, copper is always in FCC, but under some extreme conditions, we can even have copper in like BCC. So in this kind of cases, how reliable is the free energy which you predict from CALPHAD? That's my first question. And my second question is that for the kinetic models, so you have it's in the precipitcal. So interfacial energy is one of the key parameters. But many times I assume I see like people use the interfacial energy as a constant instead of as a function of temperature. How strong will this assumption affect the later kinetics? Thank you.
Yeah, certainly. On the second question, under the protocols we developed in that NASA project, the critical undercooling measurement is giving us the interfacial energy at one temperature. And similarly, we will then run coarsening measurements at larger particle sizes to get the incoherent interfacial energy. And similarly, that's at one temperature. And then in practice, we estimate a typical value of the surface entropy term. So in practice, that's what we do. I think if we really needed to know those quantities over a much wider temperature range, I think it would be important to find ways to make a measurement at 2 temperatures to get a better value for the entropy. But I would say at the moment, it doesn't look like that's really holding us back. As far as I did talk about the procedures we follow to improve accuracy. In the context of a particular engineering project, we assess different databases to select the most accurate for a given attribute. That example of the IGT single crystal alloy, we used one database for the solid liquid partitioning and another company's database for the molar volume. By just down selecting the best for each attribute that went into the design. And then of course, the calibration strategies where as we get experimental data to actually feed back by putting energy shifts on free energies, for example. So I think there are ways that, and I think it's very important as we build the higher level tools on top of CALPHAD that we have to have in those tools the tuning knobs that we can take feedback from prototyping to adjust in the composition region of interest to have even greater accuracy in our predictions. But as far as the extreme processing conditions that are so far from equilibrium in additive manufacturing, perhaps I could put a slide up on that. Let me see, actually though.
Yeah, you can share slide.
Yeah, I gotta go open it up again though. Let me, I think I closed yeah, I did. I gotta go back. Wait a minute. I gotta move some things around. Oh, here we are. Am I sharing?
Yes.
Yes.
Yeah, here's a good example. Yeah, so this is now using a macroscopic process simulation of 3D printing by a laser-based process applied to a Questec stainless marging steel. And of course, the first thing that's extreme about laser fusion is these melts are actually taking to the boiling point that we don't usually do in the processing of alloys. But this is the output from the process model of the actual cyclical temperature time conditions, which are pretty extreme in the excursions and temperature, the cooling rates involved, but we can simulate those things. And then in this case, we use the original Questec PrecipiCalc code driven by that temperature time cycle. And this shows how initially very stable oxides in this system are fully dissolved. They precipitate and dissolve again and reprecipitate. And at the result of that complex processing in terms of number density and observed particle size, we actually have quite good agreement for the mixed titanium, aluminum, corundum oxides in the system. And this is the one attribute of microstructure that's sensitive to that early process history that is retained throughout the rest of processing. In particular, where it's advantageous is these very stable oxides are a good grain refining dispersion during the very high temperature HIP consolidation that we apply to these 3D printed materials. So we can keep reasonable grain sizes after HIP consolidation. So pretty extreme. Interestingly, the student who ran this simulation went to the literature and just picked a value from the literature for the solid liquid interfacial energy in an iron-based melt. And we tried it, worked very well.
Oh, yeah, very nice.
Yeah. So hard to imagine something more extreme that we would have to try to model with our CALPHAD tools. Right?
Can I ask one more short question?
Sure.
Okay. So yeah, I see in the structure in which you talked about this ICME based or multi-scale based modeling thing, I saw an underrepresentation of phase field. So phase field which people can use to predict microstructures. So my question is how does this phase field modeling will fit in the framework which you have in Questec and then in Apple? So do they actually use phase field modeling technique to predict microstructure, or they directly go with experiments and things?
The short answer is no. You know, if you really want to have pictures you can look at of microstructure, phase field is an efficient technique provided you use unnaturally diffuse interfaces. And then you can question the realism of that approximation. But if you think about it, the role of micrographs in material science is to measure numbers. And what we want is the numbers. Our structure property relations are based on the numbers we measure from micrographs. And so from the start, to support this technology, PrecipiCalc was conceived as a tool that would not give us pictures, but give us the numbers we want to know. So we get out particle size distributions, and we can put that directly into our structure property relations. And we don't need to see the picture. We have a pretty good idea what it looks like, right? We got the models that give us a grain size, that give us the particle sizes, and all these things are evolving at different stages of processing. And what are the tools that get us directly to the numbers that go into structure property relations? And that's far more efficient than trying to build out 3D microstructure representations.
All right, okay.
Thank you.
Yeah, let's get into the next question. So the next one would be the Tajuddin from Single Band. So yeah, so Tajuddin, we probably should chat offline, you know, because I used to work at Single Band for 80 years. So Tajuddin, it's your
great, thank you.
Please share your camera first.
Actually, my camera is not working, so I'm sitting in
fine.
a dark place, so that's the problem. Sorry.
Yeah, go ahead.
Okay, so my question is, you have told that you're already working on developing some internal database, thermodynamic database for your own application. But are you also working on developing some diffusion database? So then it will be more useful.
Are you asking about database development at Questec?
At Apple. Yes, yes.
Certainly. As Jim Yurko mentioned, we had Wei-Ming Wang. She still may be the best CalPHAD assessor on the planet. I don't know if anybody wants to debate that topic. So a lot of what we have at Questac really started from her. Under the TriMet Center, of course, we have direct collaboration with NIST, and Carrie Campbell is really in charge of the mobility database building. And there, right now, the activity focuses on cobalt alloys as the next class of super alloy that we're looking to develop to try to outperform the nickel alloy. So we are building a large public database, a thermodynamic database for cobalt, as well as mobility database and molar volume database to support gamma prime cobalt superalloy design for ultimately single crystal applications, but also printable cobalt alloys that we may be able to outperform printable nickel with printable cobalt, taking advantage of slower diffusion in cobalt to have more quench suppressibility during deposition.
Thank you very much. So can I ask one more question? Actually, I want to share one of my experience. So can I?
Sure.
So initially, I was completely focusing on thermodynamic calculations for product development or alloy development. So now I'm working in some ceramic system where I have seen that if we can combine artificial intelligence with CALPHAD, then it really gives some tremendous the prediction quality. So are you also doing this kind of some stuff? I'm not actually using artificial intelligence to develop some database, but what I am doing. So suppose I'm using that process condition as an input, then some phase. I'm not using that oxides or that composition instead of that. So I'm converting that into some phases or some other parameters. Then that I'm using as an input parameters for the deep learning models. From there, I'm trying to correlate with that output property. So it is actually giving some fantastic output. So
yeah,
how do you
certainly
think about this approach?
It is one of the themes of our TriMed university research to explore the best ways to integrate machine learning into CalPHAD-based predictive design. But I essentially interpret AI as applied ignorance. Really, we have tremendous predictive knowledge in physical metallurgy, and it's a big mistake to ignore it and build an empirical correlation to replace it, right? That's moving backwards. Empirical correlation is great in fields like the social sciences that have zero mechanistic understanding. So there's nothing but correlation. So fine for them, and it's worked well for them. For us, number one, we generally don't have big data, so big data tools aren't really relevant. But what we do have is fundamental data, right? So we have the CalPHAD fundamental data, and so what we're looking at is the hybrid strategy. As you look at new superficial data, how do you transform that data using CalPHAD-based parameters and then mine correlations there to get when you'd like to improve the accuracy of a structure property relation, for example. And the value of doing that is now, instead of something limited to interpolation, because you've calibrated to fundamental CalPHAD accessible parameters, now you've got a calibration of a predictive model that can make predictions outside the range of the data that calibrated it. So I think the current research frontier is the best hybrid strategies to combine new information with existing fundamental data and adapt our data mining strategies to that. And that's the kind of research that we're doing right now.
Thank you very much. Thank you.
All right. Okay, that's great. So the next question will from Za Urando Tree. I don't know if I pronounce your name correct. Please share your camera and ask your question. So Za Urando Tree, are you there?
Hi,
Hello.
hello. Hi, it's Yuan.
Oh, okay. You are-
So, okay, long time no see. Okay, Greg, so you said you could answer some question about Apple. So
I can try, yes.
Yeah, a very general question is about what materials or what specific design method Questech provided to Apple or something they are using for their products or something. Very general question.
Yeah, I think that, you know, I can repeat things that Jim has said in his public presentations, you know. So,
Yes, yeah,
we did-
because I know
yeah, we did
James
have
talk a lot about many things about the aluminum, titanium, and 316L stainless steel.
Yes.
Something about that. Yeah.
Yeah, so as far as the methodology, I mean, it was an experienced design team that went from Questech to Apple using the methods and tools that we use at Questech that already had been applied across a broad range of materials. But of course, they were interested at the time in the Apple Watch materials
Okay.
and the anodizable 7000 aluminum was actually, in the first iteration was was done at Questech before the acquisition to demonstrate
great.
the methodology. And of course, the specific gold watch alloy was a very unique design. So it was the methods that we continue to use at Questech that are being used inside Apple. And in fact, in honor of my 70th birthday, they invited me to Apple, and the guys were, you know, cleared to give presentations of exactly the procedures by which they designed all of the Apple Watch alloys, as well as the other iPhone materials of the time. So it's the same methods, but of course our methods are driven primarily for mechanical properties, which are very important to Apple. But as Jim emphasized, cosmetics is probably even more important than structural performance. And so the guys really had to hurry up and build the models of the aesthetics. And the big challenge in 7000 aluminum was to modify it in a way that it was anodizable. That was the biggest challenge of the development of their 7000 alloy. So it's quite another dimension to build aesthetics models.
Okay, so one more very small question. Many times, Jim and you mentioned about high throughput method. Is it high throughput method that the JC used a lot of diffusion multiple or something else?
Well, I think the things he demonstrated is one approach, and it does allow a fair amount of parallelism to it. So certainly building off what he's demonstrated is one of the things we're interested in. Actually, our planned research right now is focusing on the grain boundary genome. So we really want to get the data on grain boundary segregation, starting in steels, where we did a lot with DFT on that I talked about, but that was from the viewpoint of individual components. We really need to look at co-segregation in grain boundary, which means the interaction energies in the grain boundary phase. So we're looking at ways to rapidly map that out right now. We're also looking at the liquid state. There's a lot that Antoine Alenor at MIT would like to do in getting a lot more data on metallic melts, taking into account the short range order in those melts and properties like viscosity we'd like to be able to predict much more accurately.
Okay, thank you very much. Yeah.
So at the moment, we're as far as exploring the new techniques to measure things, we're doing it in a way that's driven by steel design and what are the other parameters we want more accuracy in steel. But once again, we like to use steel as the first test case, but build methodologies that are much more general.
Okay, thanks. Yeah.
All right. Okay. So next will be the question from JC. JC, you are online.
Yes, yes. Gotta be careful what I say about this man.
Thank you very much, Greg, for the excellent talk, and it's always inspiring. I think I agree with you. Some like a Genome 2.0 should really focus on database and fundamental database development. I think the thermodynamic database, for some dialogue.
I should ask you to estimate, what do you think the cost of a tie line is right now with your methods?
Depends on the system, so for the low temperature ones, like aluminum, we can probably, get down to, I don't know, maybe $10 a tie line or something like that.
That's good. You've only got another order of magnitude to go.
But for high temperature one, depends on,
Yeah.
how long the heat treatment is. But we do have a lot of ideas how to accelerate those things in the future. I think I hope that the folks will come to my talk next Thursday. I can share some ideas about how to build databases. We recently did a lot of work on the mobility databases, how to accelerate that and how to make it more robust and less parameters. And, that's, I think, how it's going to have a good impact on. So what we found is that the mobility actually behave much more regular than we think after the thermodynamic database gets set up really properly. I think that's really some really good news in that front. So, yeah.
Yeah, I will say that, under that NASA project, when we put together diffusion couples between complex disk alloys and pure nickel and looked at the predictions, knowing that, even in the Smithell's handbook, the uncertainty of a diffusivity is like a factor of 3, right? So there's big error bars on the input that we build these things on. I was absolutely amazed at the accuracy of the prediction of coming out of a complex system. It was a surprise to me. We really didn't have to adjust things very much at all. Yeah.
Yeah, and taking what Anderson and the Young Ogren established this atomic mobility, really just a wonderful, wonderful tool to
very important.
Yeah, that's so important to move from the pure elements to binaries and the multi-component systems. So I think that's the power of CALPHAD is that kind of simple but the semi-fundamental models that you only need a couple of parameters. But
well, I think it's a good thing that it was developed early enough that computers were very weak at the time. So there was no choice but to build a very efficient, as simple as possible structure. And that efficiency has been extremely important in the further development of it.
Yeah,
and something we want to keep, right?
Yes. Without that, you can imagine, each of the multi-component system at any composition, any temperature is a different parameter, and to fit that parameter just insane, right? It's completely impossible. All right, that's just my comment.
Can I have a question?
Yeah, go ahead.
Okay. Well, Greg, I really want to thank you for this wonderful presentation. And I think the CALPHAD community becomes more and more important. Would not be today without Greg's continuous support and promotion for the last 40 years. Or 50 years, or 40 years, well, when we moved across Western.
Now you can thank Elon Musk.
Well, no. I think what happens is that Elon Musk is influenced by you, and without you, probably he would not understand how important CALPHAD is for materials design and for for accelerating the deployment of new materials. I think we owe Greg a huge thank, and thank you very much, Greg.
You're very welcome. But I will say, I had this exhilarating opportunity of being invited out to give Elon Musk a half-hour elevator pitch, and it was really fantastic how much he wanted to know the science behind the method. How many CEOs would want to know the science? And he asked very good questions, and he bought it, completely. And his own opinion about empirical development of materials, he used the F word about 5 times. So he wanted nothing to do with it. Okay, no empiricism for him. Predict it from science, and that's what CALPHAD's enabling. And he's really taken it and run with it. It's beautiful to see what he's done with it. Yeah.
Yeah, I do want to mention that, as JC mentioned, that your talk is always inspiring. I still remember that my first time listening to your talk was 1988 in Stockholm. That was 40 years ago, more than 40 years ago now. Yeah. And it's always inspiring to listen to your talk. Thank you, Greg. Thank you very much indeed.
I live to corrupt young minds. That's right.
Influence. Let's make it positive.
Yeah.
Thank you.
Okay.
All right. Okay. So thank you very much, Greg, and thank you everyone for attending this third plenary talk session. So
and
Greg,
I will see you all at MIT in 2 years. How's that?
Yeah. Yeah. So Greg, I hope that you can also go to the Gather Town. So after this Q&A session, we actually have this extended Q&A session, so people can have more casual discussion with you there.
Okay, I will try to do that again. So.
Yeah.
All right.
All right. Okay, that is great. So that's essentially conclude our session today. Yeah, thank you everyone. Looking forward to see all of you for the next one, which is also on next Thursday, the same time. Okay, see you all. Yeah, thank you. Yeah, bye-bye.
Take care.
Yeah.
Thank you.
Bye.